Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, welcome to a course called Fundamentals of Atomic Force Microscopy. This is a two-part course that's offered by Purdue University under a nanoHUB-U initiative to try and disseminate information to an audience much broader than just those students that are in residence here at Purdue University. So today what I'd like to do is I'd like to start this course by having a general discussion of intramolecular and intermolecular interactions and sort of set the stage for what we're going to cover in the first week of the lecture. Before I do that, it's probably worth briefly summarizing what the first part of this course is all about. And of course, it's about an atomic force microscope. And we're going to cover some basic elements of the atomic force microscope as I've indicated in this particular slide. And since we have 5 weeks to cover the first part of the course, there are roughly going to be 5 topics that we're going to discuss. First topic discussed in the week 1 of the course is a rather in-depth discussion of the forces that result between a tip and a substrate. And to calculate those forces that result between a tip and a substrate, we're going to have to do a rather detailed discussion of interactions between atoms in the tip and atoms or molecules in the substrate. So that's the point of the first week of the course. Week 2, we're going to integrate those interaction forces that we discuss in week 1. We're going to integrate those to actually come up with expressions for the interaction potential energies between the tip and the substrate. And we're also going to discuss some of the properties of a substrate that are important in any atomic force microscope example. So that'll be covered in week 2 of the course. In week 3, we're going to talk about how these forces are transduced and measured by a simple cantilever which acts as a force sensor in an atomic force microscope. So in week 3, we're going to spend some time on interaction forces as measured by the cantilever. We're going to discuss the physics and the mechanics of the cantilever. Week 4 is going to be a discussion roughly of the entire AFM system. So we'll talk about how the forces measured by the cantilever are finally read out using this 4-quadrant photo detector. We're going to talk about interactions between the tip and the substrate and how they're measured experimentally. We're going to talk about how that data is interpreted in roughly the 4th week of this course. And then interleaved between all these discussions, we're going to do some numerical simulations based on this VEDA algorithm that's been developed here at Purdue by Professor Raman and his group. So comprised all together, these are the aspects of the part 1 of this course that will be discussed. If you viewed the scientific overview for this course that was presented on the web page, this was available for you to look at, hopefully motivate you to register for the course. We had a rather comprehensive bubble diagram that showed the various aspects of atomic force microscopy that will be discussed. That bubble diagram was intended to be comprehensive. What I'd like to do now is just emphasize to you that for week 1 of the course, we're really going to focus on tip sample interactions. And in particular, we're going to focus on the interactions between individual atoms and molecules, one with respect to another. We're going to try to sort out how those interactions vary as a function of the separation between the various atoms and molecules. So this forms a very basic, fundamental discussion that nicely lays the way to calculations of tip sample interaction forces, which is, of course, what atomic force microscopy really measures. Let me say up front that all of these interactions that we're going to talk about in week 1 are electrostatic in nature. They all can be traced back to application of Coulomb's law. This is presumably familiar to all of you from your introductory course in physics. Coulomb's law just says that if you have 2 point charges, Q1 and Q2, those point charges are separated by a distance z, then there's an electrostatic force between the 2 charges. That electrostatic force varies as 1 over the distance squared, 1 over z squared, times the product of Q1 and Q2. These forces can be measured inside of a material or a medium which has a dielectric constant kappa. So if these 2 charges are embedded, let's say in a liquid or in a solid, the interaction force that's experienced between the 2 charges is reduced by this parameter kappa. So that's also something that has to be taken into account when we discuss the interaction between point charges. So fundamentally, this is the classical picture of electrostatic interactions, and it's going to form the basis of our discussion throughout the first week of this course. I'd also like to emphasize another concept from your introductory course in electricity that's electrostatics that's very important, and this is a discussion about how much energy is required to assemble charges. So you might recall that if you have 2 charges, one that is fixed called Q1, and another one that is movable called Q2, right? There's a certain amount of work required to move charge Q2 in the presence of charge Q1. So if we start Q2 at some position far to the right, and we want to relocate that charge to, let's say, some final position that's a distance z from charge Q1, a certain amount of work is required, and that work is defined to be the integral of the force exerted dotted into the line integral, or dotted into the path vector dl that the charge Q2 moves through. We have to integrate those force, those components of work over the entire length of the path from some initial position, which is usually chosen to be infinity, to some final position, which is usually chosen to be z in this set of lectures. So once that work is calculated, right, we can then formulate something called the electrostatic potential energy. That's how much energy this final charge distribution has assumed after it's been assembled. And that interaction, that electrostatic interaction potential energy will be referred to as capital U. It'll be a function of the distance of separation between the charges involved, and it's defined to be the negative of the work that's required to push the charges into place. The other thing that we're going to assume is that once the charges are in their final resting place, they are stuck down, so they're not free to move under the electrostatic forces that are exerted by these charges. So this is also something that we just assume you understand. The charges are always basically stuck down into their final positions. And we're more interested in calculating how much energy is required to assemble the charges into a final orientation. The interaction potential energy is useful because if you take the negative derivative of the interaction potential energy, you'll get the force that acts on these charges. So, for instance, if you have, in the case of 2 point charges, the interaction potential energy varies as 1 over the separation between the two charges. And it depends on the product of the 2 charges, Q1 and Q2. Coulomb's law can be straightforwardly recovered from this expression by just taking the negative derivative of it, as I've indicated in the last equation on this particular slide. Now, it's important for you to remember that this quantity U is a signed quantity. The value, the polarity, the sign of U, whether it's positive or negative, depends on the polarity of the charges involved in the discussion. And I try to make this case explicit in this particular diagram, where I show a charge capital Q, which is fixed at the origin of some coordinate system. And then I have two movable charges located far away to the far right of this indicated to the far right in this diagram. These two movable charges have opposite polarities, plus Q and minus Q. And what we like to do is we like to consider the motion of each charge in turn and try to see how the electrostatic potential energy varies as we move it closer to the fixed charge capital Q. And again, this is just a reminder that if the polarity of the two charges are the same, so that means if Q, capital Q and small q are both positive or both negative, the electrostatic potential energy increases as we move the two charges close to one another. And that's indicated by the red upward curve in this particular diagram. That upward curve, or that red curve, increases as 1 over z, where z is the separation between the two charges. Conversely, if the polarity of the two charges is opposite, right, then the interaction potential energy will decrease. And we'll follow the blue curve indicated in this diagram, right? The interaction potential energy becomes negative, and that indicates that the final configuration of charges is in a lower potential energy state than it was at the beginning of the calculation when the two charges were far apart. So nature always tends to go to the lowest energy state, and so given a choice, if the electrostatic potential energy is negative, that indicates that that's an attractive type of interaction that the charges in question will tend to go to a final position if left to their own motions. I think it's important up front to discuss the difference between intramolecular interactions and intermolecular interactions. And in particular, how these intramolecular and intermolecular interactions influence the electrostatic potential energy, for instance, in the case of, let's say, a molecule. So to start this discussion, let's focus on the intramolecular interactions. These are the forces or the interaction potential energies that are appropriate for charges inside of a molecule. And to pick a molecule to start a discussion, let's pick the simplest one, the hydrogen molecule. The hydrogen molecule is comprised, the hydrogen atom, of course, is comprised of one electron, one proton to form a hydrogen atom. Hydrogen molecule is two hydrogen atoms pushed up one next to the other by some distance. If you just calculate the electrostatic potential energy interactions between the various parts of the atoms, you'll find that there are four contributions that must be taken into account. So first of all, this is a quantum mechanical calculation in principle, because the electrons are delocalized around the nucleus of each hydrogen atom. Those electrons have to be represented by wave functions, and those wave functions are schematically shown in this diagram by a spherically symmetric electron charge cloud. But what can happen is the two atoms are brought close to one another. The nuclei, the positive nuclei of the two atoms can repel each other. That's a repulsive interaction, and that would have to be taken into account. Likewise, the two electrons associated with each hydrogen atom, those electrons have negative charge, so negative charges will repel, and they will produce a repulsive interaction as the two atoms are pushed closer one to another. To counteract those repulsive interactions, there's going to be an attractive interaction between the electron and the atom on the left and the nucleus of the atom on the right. That would be an attractive interaction. And likewise, the nucleus on the right could interact with the electron cloud on the left, producing an attractive interaction. And to calculate whether the hydrogen atom has a stable, to calculate whether the hydrogen molecule has a stable separation between the two hydrogen atoms, you have to calculate the electrostatic interaction potential energies including these four cases. You have to sum them up, And if there's a minimum in the electrostatic potential energy, then that minimum, the location of that minimum, tells you where one hydrogen atom is going to be located with respect to the other. So that whole process is schematically indicated by the graph on the bottom of this view graph. In particular, we're focused on the dashed curve, right? The dashed curve shows the typical electrostatic interaction potential energy between these two hydrogen atoms as they're brought close to one another. And as you can see, there is a well-defined minimum. That well-defined minimum is at about minus 4.5 electron volts. And it occurs when the two hydrogen atoms are about 75 picometers apart. So that then defines the equilibrium separation between the two hydrogen atoms. And that then leads to this stable hydrogen molecule. So this whole process is referred to as chemical bonding in a generic way. Our chemistry colleagues who may be sitting in on these lectures understand this phenomenon very well. I'd just like to say that this chemical bonding is really a continuum, right? It spans a wide range that goes from a totally covalent bond in which electrons are equally shared between two atoms, two or more atoms in a molecule, to the case of an ionic bond where an electron is literally transferred from one atom to the other. In between, there's a whole range of bonding that can occur. I like to refer to it as a dipolar covalent bond, right? It just means that there's unequal electron sharing between the similar atoms in a molecule. And this unequal electron bonding, or this unequal electron sharing, gives rise to a permanent electric dipole moment, which in these lectures are referred to as by the symbol P. So this permanent electric dipole moment is indicated by this elliptical shaped object. It indicates that one end of the molecule is slightly positive, the other end of the molecule is slightly negative, and this separation of charge due to this dipolar covalent bonding gives rise to dipole moments. And these dipole moments are then free to interact one with respect to another to produce a net attractive or repulsive interaction. And ultimately, these dipole moments are going to lead to interactive forces between a tip and a substrate in atomic force microscopy. So these are things that you probably understand if you've taken an introductory course in chemistry. But I just thought it would be worthwhile to summarize these ideas in this first lecture of week 1. How do you decide which way electrons go in a particular molecule? Well, that's decided on the basis of the electronegativity of the individual atoms that comprise the molecule. The chemists have characterized this quantity called electronegativity, and I like to refer to this chart, which I use very often in my own research, because it takes the periodic table of elements and it distorts it in such a way that it puts the elements that have highest electronegativity highest in the chart. So fluorine and oxygen and nitrogen protrude up higher than all the other elements. They have the highest electronegativities. And it's very easily, you can very easily compare electronegativities of different elements by just referring to their relative positions in this particular chart. I've indicated some horizontal red lines that are more a guide to the eye. And what I always like to point out is that if you look at the horizontal red line that goes through hydrogen, it also intersects very nearly the carbon atom, And this just means that the electronegativity of hydrogen and carbon are about the same. And this would then lead you to predict that many hydrocarbons that are formed from hydrogen and carbon will not have a dielectric dipole will not have an electric dipole associated with them, because the electronegativities of these two elements are essentially the same. To reinforce this notion of transfer of electrons, I just make up some very simple schematic diagrams which try to show how the electrons are transferred when two hydrogen atoms are brought one to another. The two hydrogen atoms have the same electronegativity, so in principle the electrons don't have a strong preference on which way to go. And in practice what they do is they pile up symmetrically in the space between the two nuclei of the atoms, and this symmetric pileup, of course, gives rise to the chemical bond that holds the two hydrogen atoms together. This should be contrasted to the case of hydrogen fluoride, where fluorine is a very electronegative element. It will tend to pull the electron from the hydrogen into its influence. That means that the fluorine atom will become negatively charged, the hydrogen atom will become slightly positively charged, and you would then expect the hydrogen fluoride molecule to have a dipole moment somehow, as I've shown schematically in the diagram in the bottom right of this particular slide. So these are just simple ideas that follow from the discussion that we've just had. It's a fair question how you, if given a particular molecule, how you might calculate the dipole moment of that particular molecule. And in this diagram, I just try to remind you of the general case. The answer to the question is, how do you calculate the dipole moment for a molecule? Well, that calculation requires you to know 4 quantities. 3 of the quantities are the x, y, z coordinates of each atom in the molecule. That's indicated by the parameters x sub I, y sub I, z sub I in this particular diagram. The 4th quantity you need to know is a parameter that's referred to as A. A is the number that tells you the partial charge that each atom in the molecule possesses. So A is a number that ranges between -1 and +1. And this quantity A is often the result of some quantum mechanical molecular structure calculation. So you can find tables of the coordinates and tables of A's for different molecules on the web. And once you know those coordinates and those values of A for each atom in the molecule, you can then calculate the dipole moment in the x, the y, and the z direction as I've indicated. And then lastly, you can calculate the magnitude of the dipole moment by taking the sum of the squares of the dipole moments in the x, y, and z direction. So I've also indicated that important result in this slide. So I think that ends our discussion of intramolecular forces. Intermolecular interactions are going to result because atoms or molecules that have dipole moments start to electrostatically interact one with respect to another. And the strength of those intermolecular forces are going to determine things like boiling points, surface tensions, and viscosities of liquids. And so these subtle dipole-dipole interactions actually manifest themselves in these physical quantities. And it's probably worthwhile to just remind you of some simple facts. And that's gonna form the basis of lecture 2. We'll actually show you how these various quantities depend on the size of the dipole moments in each of the molecules that are considered. But ultimately, these intermolecular interactions all occur because molecules or atoms interact one with another by a wide variety of different electrostatic interactions. You can have the Coulomb interactions between point charges. These would correspond to ion-ion interactions. You can have atoms or molecules that have permanent dipoles associated with them. These would then give rise to dipole-dipole interactions. The electric field from one molecule could induce a dipole moment in another molecule. This is referred to as induction, and that induced dipole moment would then cause a net positive or a net attractive interaction between the two molecules. And then lastly, you have the possibility that there can be dipole fluctuations in nonpolar molecules, in molecules that have no permanent dipole moment. And these dipole fluctuations can then give rise to a net interaction between nonpolar molecules. We're going to systematically work through all these interactions. I think it's a worthwhile exercise to go through. It gives you a much clearer understanding of the nature of intermolecular forces, and the nature of these forces ultimately give rise to the interaction between a tip and a substrate that's relevant for atomic force microscopy. So that's the end of the first lecture in week 1. Come on back for lecture 2, and we'll continue this discussion in some interesting ways.